welcome back. Today is the day 2 of week 5. So we have been discussing about the D4 point group, and we were trying to find its character table, form its character table completely. So where we left yesterday is at this particular place. So we took, we formed this one-dimensional representation. We saw that it has 4 one-dimensional irreducible representation, and taking the orthogonality into consideration, we found the 4 irreducible representations starting from gamma 1 to gamma 4, and knowing that the 5th one is a 2-dimensional representation, we took xy axis as my basis and operated all the symmetry operations, and we found the matrix forms of those symmetry operations using xy as basis set, and thereby we got the characters of those particular symmetry particular representations, right. So these were our results. So for identity we have character 2. Now we already knew that, right. There is nothing surprising about that, and we already wrote that. And for C4, the class for C4, it gives the character as 0. So let's put that, and C2Z gives -2, and C2X as well as C2 prime XY both gives character as 0. Okay. So seemingly we have got our character table completely for area 1 and area 2, but we have to yet check that. So first let's see if the square of the characters of this particular irreducible representation, which is 2-dimensional, whether it is equal to the order of the group or not. So very easily we can see that it is 8. The square of 2 plus square of 2 equals to 8. So that is satisfied. The last thing we are left with is to verify whether orthogonality holds or not. So similarly, similar to the previous example where we check the orthogonality between, I think, gamma 3 and gamma 4, here we will check the orthogonality between gamma 5 and say gamma 4 as one of the IRs. So if I do that, then what we have, 2 into 1 equals to 2 plus 0 into -1 into 2 equals to 0, then 1 into -2 equals to -2, and then 2 into -1 into 0 equals to 0, and again 2 into 1 into 0 equals to 0. So ultimately we have 0. So this gamma 5 is orthogonal to gamma 4, and I will leave it with you that you verify if this one is orthogonal to any one of them. Okay. Actually, you will find that yes, it is orthogonal. Gamma 5 is orthogonal to any of the other 4 IRs. Okay, and all the IRs are orthogonal to each other, and they are normalized to the order of the group. So we have successfully found the irreducible representations for this point group D4. Now at this point, let's complete both area 1 and area 2. So here we are supposed to give them the Mulliken symbol. So if I look at this, is totally symmetric irreducible representation, of course it will be A type. Now there are other A type representations there. Also we can see there are B types. Okay, so I am not going to talk in detail about this one because we have already discussed about Mulliken symbols for irreducible representations in detail earlier. So here with respect to principal axis of symmetry, these two are symmetric. So without worrying about anything, these two will be given the notations A. We will worry about subscript or superscripts later, and these two one-dimensional representations are, if I look at the characters correspond to this principal axis of rotation, I find that as antisymmetric. Therefore, these two belong to B type of symbol. And this one being a two-dimensional representation, we have E as the symbol for the IR. And since there are no center of inversion, we don't have to worry about whether there are G or EU subscript for this one. Neither we have another two-dimensional representation, so we don't have to separate two different E type of representations. So E will remain as such. Only we have to worry about A and B's. So here, what is our notion? Our notion is to look at the symmetries of the character with respect to the perpendicular C2s, right? So when we want to differentiate between these two IRs, we look at this C2 primes. So we see that this one is symmetric while this is anti-symmetric. So this one will be A1 and this one will be A2. Similarly, if we want to differentiate between these two B's, then I look at again here. So with respect to this one and this one, I have this one as anti-symmetric, this one is symmetric. So I can write this is as B1 and this is as B2, okay, and this remains E. So I got the Mulliken symbols as well. So now what we are supposed to do here is to find out what will happen to the other two areas of the character tables. So I have area 3 and area 4. Okay. So we may not be able to complete the whole thing, but we will start, and rest of the things you should complete as an assignment. All right. So this is area 3 where we have the Cartesian coordinates and the rotational symmetric coordinates as the basis functions. So we need to know, say x, this contains x, y, z, rx, ry and rz. These 6 functions you will find in this region. Now our job is to ascribe this x, y, z or rx, ry, rz to particular IRs, okay, which transform as one of these coordinates or the rotational coordinates. So first, if we look at the z, okay, so just the z axis, if you look at and you operate on operate all these symmetry operations, what you will find that with respect to E, C4 and C2z, okay, the characters will be 1, because this will give you one dimensional matrix, because this is only one single function, right, that will act as a basis function. So I will get character 1, 1 and 1 for this. Now for C2x, suppose, what will C2x do? C2x will change z to minus z, correct? So will be done by C2y. So that will give you a minus 1 as character. So this is minus 1, and C2 prime, okay, what we will do? That will also do the same thing. So because all C2s are perpendicular to this z axis, correct? So all these C2 primes or C2s will convert z plus z to minus z. So this one as well will get as minus 1. So now these are the characters that you get when you use z as the basis vector. Therefore you just compare this one with this 4 one-dimensional irreducible representations, and you see that this matches exactly with this one, correct? That means this A2 irreducible representation, okay, it contains z as its basis function. So we ascribe z here, okay, and what we say that this z transforms as A2, all right. Now xy we have just done, right, because xy if you remember those matrices that we formed, one thing probably I missed out, that is those 2 by 2 matrices that we found for when we took x y as a basis functions. Then those matrices, they are not reducible, okay, because they are not block factored in the same way. So you have 1 0 0 1, and then you have 0 1 1 0. So they are definitely not block factored in the same way. So that means this 2 by 2 matrices, they themselves are the blocks which cannot be reduced any further, and that's why we could use that as irreducible representation. Okay. So there we found that x y together form the basis excuse me, for this 2-dimensional irreducible representation E. So what we can write, x y okay. So whenever you see this one, then you will realize that x and y are not separable, and together they form the basis. So individual x or y cannot form a basis for any of the irreducible representation for this particular point group. For any other point point group, it may form, okay, but in this particular case they are not capable of forming as work as basis function individually. Okay, they transform together as E. All right. So what about the Rx, Ry, Rz? So what is Rz? Rz is the rotation about the z axis. So suppose I have this is my coordinate system again, while this is x, y and z axis. So this will be my Rz. So this is the rotation about z axis, okay, in a particular direction. Suppose I have, this is my direction, okay, exactly like what I showed here. Now when I operate E, nothing happens to this particular directionality of the arrow. C4, C2Z also retain the same direction of this arrow, while we apply C2X. So C2X is along this axis. So what will happen? This will come down here, okay. So if it comes down here, it will be like this, which is just the opposite. So if this one I call symmetric, then this is anti-symmetric. So what does that mean? That will give me a an one-dimensional representation which gives a character of -1. Okay. So if I look at here for C2y, that also will be giving the same character. So what I will get, just like for z, when I am looking at Rz, I got symmetric one-dimensional characters for E, C4 and C2, while for C2 I am getting -1, and if I apply the C2xy, so this one, or C2 so this one is C2 prime xy, and this one is C2 prime xy bar, both of them will act in the same way. So I will get -1 here, because these two will also change the directionality of this arrow here, which signifies the rotation about z axis in a particular direction. So this one also is the same as A2. So I have Rz also ascribed to this particular IR. Now you can find out about Rx and Ry. Okay, so that is left as as a home task. So you can try this out. Now this is area 3, and then area 4. Area 4 you will find you have either square functions or some binary functions. For example, like z square or x square plus y square, or x square minus y square, or xz, xy, yz, this. So you can probably easily see that these functions are related to the wave function of d orbital. So this part which contains something like or this kind of functions, square functions, or like binary functions like this. This particular functions are chosen because they contain the symmetries of d orbitals, different d orbitals, and this is used in case of different type of bonding. Okay, and when we will use combination of different ligands to form symmetry adapted linear combinations, we will see how useful they can be. Okay, and particularly like organometallic chemistry, where we talk about the metal ligand bonding, where the d orbitals are really vital, and there you need to know about the dependence of the irreducible representations on this particular type of functions, square functions, okay, in order to have a proper idea about this metal ligand bonding. Okay, and in the next step about their energetics. Okay, so now suppose we want to find out to which IR this particular function x square minus y square transforms as. So this is not a very difficult thing. How? So what we can do, we can individually work on this x, y and z, okay, and then we can see how this x square minus y square, for example, changes when we apply one of these symmetry operations or all the symmetry operations. So here in this picture, if we look at and if we try to see how x and y gets changed, we have already seen that. So we can just quickly recap that. So upon E, x remains x and y remains y. So this is for E. So for C4, what happens? C4, x becomes y and y becomes minus x, right? So C4, x becomes y and y becomes minus x, all right, and C2z, x becomes minus x, y becomes minus y. So C2z, x becomes minus x, y becomes minus y. Then C2, let's take C2x, okay. So C2x will not change x, but it will change y to minus y, okay. So C2x, it will change x to x, that means it will remain unchanged, and y will become minus y. And then C2 prime xy, say for example, then what will happen? X will become y and y will become x, right? So C2 prime x y, for this x will become y and y will become x. Now if I know this one, so I can easily find out what will happen to x square minus y square. Okay, so here nothing is changing, so I will have x square minus y square when I operate E on that. Now in case of C4, if I apply C4 on x square minus y square, what's going to happen? X is becoming y. So this is becoming y square and y is becoming minus x. Okay, so it's minus x square, which is nothing but minus of x square minus y square, right? So here, for example, when you operate C to Z, then what's happening is x square minus y square is getting transformed into, so x is becoming minus x, so there is no change here, and this one also remaining unchanged. Okay, and for C to x, here your x is remaining x, so therefore, and y is becoming minus y, all right. So, and lastly, C2 prime, x is becoming y, therefore, it is y square and y is becoming x, so minus x square, which is equals to minus x square minus y square. All right. So whether this is symmetric, this transformation, that is x square minus y square to something, is symmetric with respect to E, symmetric with respect to this or not, depending on that you can get either plus 1 or minus 1. And you can see here for E, it is, suppose I write here as chi of E is equals to 1, and then chi of C4 equals to minus 1, and then chi of C2Z equals to 1, and chi of C2x is equals to 1, and chi of C2 prime equals to minus 1. Now, if I look at that and compare this chi's, so chi of E is 1, chi of C2Z is equals to 1, and chi of C4 equals to minus 1. So this definitely belongs to B symmetry, and then you have chi of C2 prime as minus 1. So if you look at that, you have this symmetry. So then x square minus y square belongs to this particular symmetry. So in the same way, what you can do, you can try out different other functions, say for example z square or xz or xy. Okay, so only what you have to do, you have to just see how that individual x or y or z gets transformed upon the operations of the symmetry operations, and then taking those, you see what is happening to the total overall function, whatever that you have, and then you find out the corresponding change. So you get the characters, and then you match with this irreducible representation that you have already formed, and then you ascribe that particular function to one of the IRs with which you you get the match. That means that particular function will transform as that particular IR that you are getting. All right. So this is how you can form the total character table. Okay. The reason we dealt with this one is that in a later stage we will go in a different way. Like knowing from this one, suppose we are given a particular type of orbital, okay, and say suppose that is dx square minus y square. So I know that okay, this particular orbital has a symmetry which gives me one particular irreducible representation for a particular point group. Okay, whatever molecule we take, we are considering, suppose we have to look at the character table of that particular point group, and then we can find out that okay, this particular ligand has this particular it transform as this particular irreducible representation, and that information we will utilize later on, that with which particular other ligand it will combine with, or which particular wave function it will combine with, because every orbital is characterized by its own wave function, right? So those things we will start looking at from the next class onwards. So what we will do, we will have a very brief introduction about the relation of group theory and quantum mechanics, and then we will start looking at how one can form the symmetry adapted linear combinations, and to look at their energetics, and then in the next step we will look at the the symmetries of molecular vibrations and see how to find out different normal modes, and then try to figure out how to find the selection rules of different transitions, vibrational and electronic. Okay, so with that I will leave you today, and we will see you on the day 3 of the week 5. Till then, thank you.